Now, let me go back a little bit to this diagram here. Now, here we are trying to look at the forces acting on this small element. So here, I think instead of using sigma x plus delta sigma x, this is stresses. I have to change it into the axial force. Axial force, this is force, plus increment in axial force, and this is axial force. And this one, I change it to axial force. We are looking at this free body diagram, and we want to derive the equilibrium equation. So on free body diagram, we must show the forces, not the stress. So there is some changes that I need to make here. So here, these are all forces, axial force. So again, this is just change in axial force when we move delta x to the other side, minus the axial force on this side, assume all tension, then plus W delta x equal to 0. So if divide with delta x, then you divide, simplify this, we divide with delta x, and then you take limit delta x is equal to 0. So what we get is, we get dpx, dp over dx equal to plus W equal to 0. Okay. So this should be the starting equation that we get. This is purely consideration of equilibrium. And next, we can represent the P in terms of the forces. So next, we look at P here. P, dP here, P, we can represent this P in terms of A multiplied with the stress. Okay. And for the stress, we can take this in terms of E epsilon from the strain displacement relations, and from the stress strain relations, we get the stress strain relation. Then further, strain displacement relations. This is strain displacement relation. So now if we put it inside here, so considering all the three basic equations, including equilibrium, so we finally get to this, what we call the strong form or the governing differential equations. So finally we get d over dx, ae du dx, plus w equal to 0. So this is the governing differential equation or the strong form. Okay, this is a strong form or the governing strong form of the problem, or the governing differential equations, where it is derived considering one small part here. When we want to solve this, you need to consider, you need to integrate. Integrate once, you get du dx, which you can get the strain, and integrate again, you can get u, which is the axial displacement. So this is the process of getting. So if you are asked to use governing differential equations for 1D bar problems using theory of elasticity, you should use these equations. Understand what is this, what is this. If they are constant, then you can take it out. If this is a constant, uniformly distributed, this is constant. But this is constant, and if the cross section is constant, then this is constant. If this is a constant, okay? W is constant. if it is UDL. Okay? If it is given some other functions as a function of x, then you have to consider that function of x. Now, briefly, I will go through the solution process with you. Then I will finish up with theory of elasticity, then go a little bit briefly on energy method. Now, once we get this, in order for us to solve problem, then we need to define the whole problem completely. We have already the governing differential equations. You need the boundary conditions. You need the boundary conditions. Okay. Now, boundary conditions have many combinations. Here fixed, here free, fixed, or here free, here fixed. Okay. So I'm going to use conditions where this is fixed or this is free. And if you have to use, if there are given other conditions, it will follow the same procedures. Okay. The important thing is you need to know if this side, we know what is u, which is u is equal to 0, or we know the stress. Here, look at the problems. If it is free, we know the stress 0 here. If it is fixed, then the stress is non-zero, but we know the displacement 0. Okay, so the combination. If I make use of this, then I have the boundary condition x is equal to 0, u is equal to 0. And if here x is equal to 0, the stress is equal to 0. So these are the things that I have. But if here if fixed, then at x is equal to L, u is equal to 0. So if we have these two boundary conditions, then I have to relate these two. So this is E du dx, x L equal to 0, or if E is constant, then du dx, x is equal to L is 0, when x is equal to L. This is for this. If I show to you just now, if you have a force here, then this is different story. Okay, stress here will be equal to P bar over A. Okay, and take note of the directions. Take note of the directions. Here, direction I show here, and this will be equal to this. If the direction is opposite, if this direction is opposite, then if you look at this and the stress, we always consider the stress like this. So the resultant stress is this. So here the boundary conditions become sigma x. When x is equal to L, it is negative P over A. Okay. So you must be able to relate to this free body diagram that you need in order to get the boundary condition of the stress. This is for this acting like this, opposite to the x direction. If this is acting not in the opposite directions, this is what I showed just now. Following these directions, then it becomes sigma P over A, not negative, but it is positive. So now continue further. Once I have this, so the next thing is you have to do the integrations. Do the integrations. So the starting is this, d over dx, AE du dx plus w equal to 0. So our aim is to get u. So you have to integrate once. If I integrate once, then the whole thing becomes plus. If this is constant, I assume the case where w is constant. Okay. Assume the case w is constant, so you have plus wx equal to 0. If I integrate, equal to a constant, not equal to 0. Or I can write it down here as d over dx, AE du dx, negative W first. So I integrate once. So I get AE du dx negative Wx plus C1. This C1 has to be determined using the constant. Then this whole thing I integrate again. Then assuming AE is constant, then I have, this is assuming AE constant and W constant. So AE multiplied with this you integrate this means you integrate this, integrate means you get this equal to negative Wx squared over 2 plus C1x plus another constant here. So the task now is to make use of the boundary conditions. The task now is to make use of the boundary conditions to determine what is C1 and C2. So to determine what is a C1 and C2, you have two choices. You need to look at what boundary condition do you have. So the first one, boundary conditions, is related to stress, meaning that this is 0. So you look at the equations where you have this. So du dx appear in this first equation here. This is the second equation. So if you consider this, take note of this. This means when x is equal to L, this is equal to 0. Okay. So if I take note of this, when x is equal to L, this is 0. So I
Prof, we can't hear you.
sorry, I don't know why the mic was suddenly off. So for a long time you cannot hear me talking. Yeah. So here, just now I was explaining what is the solution process. Okay. Can you hear me now? Yes. So I was explaining the solution process by making use of this boundary condition just now when there is no voice, suddenly the voice. There's nobody in the classroom. I don't know who go and turn off the voice. I didn't, something happened and then the mic was switch off, so sorry for that. So we make use of the boundary conditions, one here and one here. Okay. Take note of whether there is any forces applied here, so you need to consider the corresponding free body diagram to get the stress boundary conditions, and also apply these boundary conditions. So starting from here, integrate, you can get this, and use one of the boundary conditions, you can get what is C1. Okay. And after that, you use another boundary conditions, you can determine C2 to be 0. So you substitute C1 and C2, finally you get to this. Finally you get to this. Then from here, we can get the stress. We can get the stress is from here you can get the U is equations, and then the stress will be E epsilon or E du dx. Okay. E du dx. So once you get the U from here, you differentiate once dx, then you can get the equation for stress as well. So that is how we complete the solutions of a what we call 1D problem. So by doing this, we can determine, we solve completely the problem using the governing differential equation plus boundary conditions. So we solve for what is U, then we can get back to what is strain by using the strain displacement relations, and we substitute the strain multiplied with the E, we get the stress strain relations, we get the stress. So that is 1D problems, how we solve 1D problem using this governing differential equation. So these equations you need to know. And this example, AE is A constant, E constant, W constant. If they are not constant, then the integrations will become more complicated and lengthy. But the process will be the same, and you need to know how to integrate different functions of X. Okay. So basically, because I take a long time now, it's 5 o'clock, about 2 hours, I cover the theory of elasticity. Okay. So I talk about what you need to know. Theory of elasticity is one of the topics that I cover. Another topic that I also set questions is on energy method. Okay. So after this, I think I will talk on energy method. So energy method is basically a bit more simple than theory of elasticity, but some calculation might be a bit lengthy, especially when you have differentiation integrations of the energy in the solution process. So I will stop here for a while and then to see if you have any questions on this part. If you have no question, then I will proceed to brief you, okay, rather briefly on the energy method. Let me stop the recording. Any questions?